Controversial take, statistical models are basic.
You're basic.
Kind of weird coming from a statistician. I think they're overused. They are a blunt instrument that is really a poor replacement for mathematical models. There, I said it. Okay, controversial, I know. But let me explain. Now you might be asking, what are mathematical models? Good question. Thanks for asking. Leading questions such as that. I'm going to tell you in a minute, but first, let me talk about what a model is. What is a model? A model is a simplification of reality. Or put another way, it retains the essential features of the thing you're trying to represent while ignoring the non-essentials. So if you think about a model airplane, it retains the essential features for its purpose, like the basic shape of the fuselage and the wings and that sort of thing. And it ignores the non-essentials, like flying. Yeah, at least for that purpose, like a model airplane doesn't need to fly. And the same thing goes with statistical or mathematical models. We simplify the complexity of reality into a simple statement or mathematical form or statistical model or something like that. And we ignore the non-essential features. And in statistics, we call that residuals or error. And models in statistics can be used to describe things, they can be used to predict things, and they can be used to explain things. And you might be asking, what makes a model useful? Well, if it's used to describe, predict, or explain, I suppose it is useful insofar as it describes, predicts, and explains things. But I would add, and that's like a standard way that people talk about models, that's what they do, and they describe, predict, explain. We all know that. But I'm going to add one more thing. They forbid things. At least good models forbid things. They not only tell you what the model allows, but they also tell you what the model does not allow. Oh, bzz. Where's my fly swatter? Death to the fly. And that's an important point. Good models forbid things. And this is where statistical models don't do very well, because statistical models can be used to fit anything. So maybe you're trying to predict the placement of a cannonball based on angle and wind.
Bam! Slap a regression on that thing.
Or maybe you want to see if intelligence and success are related.
Bam! Slap a regression on that thing.
Or maybe you want to see if Tylenol causes autism. I can't take that one seriously, but still.
Bam! Slap a regression on that thing.
See, that's the problem with these models. They forbid practically nothing. And here's the reason that's problematic. You don't know if the model is fitting your data because your model is describing something interesting, or if it's fitting your data just because that's what statistical models are good at. It's like the idea of pareidolia. Is that the word? Let me look at pareidolia. How do you say it? Pareidolia. Pareidolia, that's the human tendency to see patterns in anything. Like if you listen to a recording backwards and you find secret messages encoded. Oh my gosh, did that just say Ringo is dead? No, it clearly said Paul McCartney. And that tendency of models to fit anything is what we call fitting propensity. Preacher, 2006, I believe. Although there have been other names for it, I just can't remember them off the top of my head. So this is super problematic. This is contrary to falsification doctrine, or Popper's logic that science ought to be falsifiable. If our statistical models can fit anything, then they're not very falsifiable. Now, some might argue, hey man, that's not fair because it's the theory that dictates the falsifiability, not the model. Okay, but why not the models too? And I'm not sure the two can be separated like that. You might even argue, ooh, this could be its own video. You might even argue that, in fact, I would argue that the mathematical representation of your model is the theory. Hey, slap that on a bumper sticker, baby. And to illustrate why statistical models fail, I'm going to use an example from woodworking. Why woodworking? Because I've been woodworking since 2010. That's one of my favorite hobbies, if not my favorite hobby. And I brought 2 pieces of wood to illustrate. This proves that I build things. Actually, I'll show you a couple pictures of things that I built. Boom, boom, boom. Now, I'm not like amazing at it, but certainly have a lot of experience in it. And a frequently discussed topic of concern among the woodworking elite, of which I am not. But one of the concerns is, what is the best method to join 2 pieces together? So you have all sorts of joints, like a lap joint and a mortise and tenon and a dado and mitered corners and lots of different ways to join pieces of wood together. But for this illustration, I'm going to use a very simple example that actually isn't realistic. We don't use this very often in woodworking, but I'm going to use it anyway. I think you would call this a face joint. Oh, yeah, a lamination or a face joint. So yeah, I'm going to illustrate that with a face joint. Again, not a very common use case in woodworking, but it'll help illustrate. So maybe you are interested in joining two pieces of wood together like this. And one thing that we know from woodworking, just from experience, is that if you do it right, the wood breaks before the glue does. So the glue is actually stronger than the wood. But that's only under certain circumstances. And if you're building something, especially like building takes a lot of time and you don't want it to fail. So this is an important thing to understand. And if it fails, it would be nice to know, did it fail because of the glue or did it fail because of the wood? Or did it fail because of how the two pieces were joined together? Were they joined together in a suboptimal way? Because you don't know whether you should go out and buy a new glue or learn a new technique for joining two pieces of wood or use a more expensive species of wood that's not as prone to break. So those are important questions. Questions upon which the world hinges and whatnot. And so I'm going to develop a scenario. And this is partially inspired by a guy named Wood by Wright. I'll leave a link in the description. He did an amazing thing. And I might even analyze his data set where he did a bunch of wood glue tests. But this is slightly different than what he did. So let's say you got these two pieces of wood. And on either side, you have maybe a hook or you have a clamp on either side. And then maybe you anchor it to a very sturdy wall, and the other end you anchor to the back of a truck, and then you use the truck to try to separate the pieces of wood. And maybe there's some way to make sure that it doesn't like twist or anything, and that the two pieces of wood remain parallel. So one way to objectively measure things and be able to develop a data set with which you can start to build a statistical model or a mathematical model is you might measure the amount of force it takes to break them. And so there's scales that look like this that you often see people use to measure luggage. You might attach that between the truck and the piece of wood, something like this. And now based on the data that you develop from this experiment, what factors most heavily influence the force it requires to separate the two pieces? So now let's develop a model, and there are three types of models. Although different people have different categorizations, this is the one that I'm going to use. There are verbal models, statistical models, and mathematical models. So a verbal model is just a description. So I'm going to just develop a simple example. My verbal model is just a verbal description of what I believe causes wood joints to fail or not fail or whatever. And so maybe I'm going to start with a verbal theory that says that the amount of force required depends on the surface area of mating faces. So again, returning to my pieces of wood, my model would state, oh, these are not flat pieces of wood. Let's do that side. So my model would say that here, there is very little overlap, so these would be easy to separate. Whereas if it were like this, there's a great deal of overlap, so it would be really hard to separate the two. So that is a verbal theory, that the force required to separate them is proportional to how much surface area the two mating surfaces have in contact. And by the way, notice I haven't said anything about the type of glue because my model doesn't care about that at this point. It just says, all right, assuming you glued them correctly using whatever glue, the amount of force required is proportional to the degree of overlap. By the way, I have not studied the physics of wood joinery. I mean, I've watched a couple YouTube videos, but most of them don't go into the theoretical rationale behind it. This is just my intuition based on experience woodworking. So the strengths of a verbal model is it's super easy to develop. All you have to do is explain what causes what. In this case, what causes overlapping wood joints to fail. But there are lots of limitations with verbal models. One is that there are lots of mathematical and statistical representations of that verbal theory. For example, you might propose that force increases linearly, or you might say it increases exponentially, or logarithmically, or sinusoidally. There's lots of different ways that you can represent that. And the problem is each of these different mathematical or statistical models are going to have different assumptions. And so your theory has allowed a whole lot of flexibility. And when there's so much flexibility, it's really hard to falsify. And if it fails, you don't know whether it failed because the mathematical model was a poor representation of the verbal model, or if the verbal model itself needs to be dismissed. And so it's kind of like the idea of p-hacking. A verbal model gives you many, many opportunities to test different versions of the model until you find something that supports your hypothesis. So that makes verbal models pretty hard to falsify. And it's also practically impossible, if not possible, to make very precise predictions. So, okay, you've got a model that says more surface area means more force. Great. So given X amount of surface area, how much force do you get? Well, verbal model can't tell you. The second type of model is a statistical model. So in statistical models, we will just kind of default to the linear model version of it. That might look like this. So maybe you suggest that force is equal to B0 plus B1 times condition plus B2 times species. So basically this is saying that force depends on the condition, which I'll talk about in a minute, as well as the species. So pine versus walnut versus oak or whatever. And let's pretend that we don't care about species, that that's just kind of a control variable. And as far as condition, maybe you have two experimental conditions. One allows for 3 inches of overlap between the mating pieces, and one allows for 1 inch of overlap. So that is a statistical representation of your verbal model. And this is where most people are in science. This is what most people do. They formulate their verbal theories and then they find a statistical representation of that. It's very powerful because it's super flexible, but it's also very generic and hard to falsify. And in this particular model, support for your hypothesis is quantified by the parameter B1. So B1 here represents the slope of condition, but because condition is a binary variable, it's just the mean difference between the two. So maybe B1 is 100. That tells you that on average, in one condition, it required 100 more pounds of force than the other condition to break the joint. And I think this starts to highlight one of the problems. These statistical parameters sometimes are kind of meaningless. So in this case, B1 is the average difference in force, which we can successfully link to our verbal hypothesis, which says the separation force is a function of how much overlap there is. And in our model, we have operationalized that overlap as condition A versus condition B and the difference between them. But the other parameters aren't really that interesting to us. So B0 represents the average force for a board with 1 inch overlap, or it could be 3 inches depending on what your computer defaults to as the referent group. So in some ways it's a little awkward, the tie from the verbal theory to the statistical model, and sometimes we end up having to force it, but still we have a problem of falsifiability. They are falsifiable, but not very falsifiable. So you might be saying, well, can't you just do a hypothesis test on the slope? And absolutely, you could. So you might do a hypothesis test where you hypothesize that the B1 parameter, or the difference between the two groups, is going to be 0, and then you do a significance test and identify, okay, if I assume they are 0, what's the probability I would retain these results? And then you could have a p-value associated with that. But the problem is that's a really low bar to pass. And let's say you do pass it. Okay, what you've concluded is that if there is 3 inches of overlap, it is significantly harder to separate than if there's 1 inch of overlap. And that does provide some support for your verbal model, but it's kind of like, meh. And in addition, without strict assumptions, it only really describes the relationship. Okay, here's the mean difference between the two groups. And we make some sort of a somewhat weak tie to the verbal theory, so therefore I support the hypothesis that surface area matters. But what if the relationship is much more complicated than just 1 inch versus 3 inch? Maybe there's some hidden complexity that we're missing. Like maybe it doesn't scale linearly. Maybe doubling the surface area doesn't double the force, but maybe it triples the force. And there's some hacks you could do with statistical models to evaluate that, but it's kind of awkward to do. In short, the model doesn't very well defend the theoretical explanation. And I would say nor does it fail to. It's kind of sort of agnostic to the theory. And I mentioned earlier, one of the problems with verbal models is there's lots of different representations, and because there's lots of different representations, if one doesn't work, you could always try another one, which makes it hard to falsify. And the same thing happens even within statistical models. So like we might have 2 different models that look like this. One proposes that all that matters is the surface area. The second one proposes that there's independent effects of width and length, and maybe an interaction effect. And at the end of the day, we're kind of left with, okay, so what? We found there is a difference between 1 inch versus 3 inches. Or we found that increasing the length of overlap means there's higher forces. So what? What do we do next? I don't know. And that brings us to mathematical models. So the good and bad thing about mathematical models is they force precision. They force precisions about what you're claiming and what your assumptions are. So a mathematical model would say, all right, force is related to surface area. How? And again, we go back to those questions that I was asking earlier. If you double the surface area, does that double the force? Does it quadruple it, or does it half it? And also, you might want to ask, is there an upper limit to it? Or not? And so mathematical models force you to confront the details of what you're trying to say. And by so doing, it increases the riskiness of your model substantially. And we want riskiness, because if our model is bad, we want to falsify it so we can work on another model. And as we add this level of specificity, all these assumptions and all these claims we make become very testable. So let's work through an example using wood. This mathematical model supposes that there are 4 important parameters that dictate how much force it requires to separate 2 pieces of wood. One is F max. So F max is the amount of force it required before failure, maybe measured in pounds or in newtons or something like that. And another parameter is tau. Why tau? Because scientific models always contain Greek symbols. And if I don't include tau, I'd be like the dude who showed up at a black tie event with a pink tie. And I don't want to do that. Social pressures from my peers, I guess. So in this hypothetical model, tau represents the amount of force required per square inch, or the shear strength per square inch. And then we've got W, which is the width of the 2 boards overlapping. And maybe that's in inches, or for our metric friends, it might be in centimeters. And O is the overlap, again in inches or centimeters, whatever, which is the amount of overlap between the 2 pieces. And so our model might look like this. F max is equal to tau times W times O. Or in other words, the force required is equal to the holding power per square inch times the width of overlap times the essentially length of overlap. Now that we have specified that mathematically, we can start to think about what are the implications of this model. So this model mathematically is saying there is no limit to force. It might require the strength of God to separate these 2 pieces. But that doesn't seem to make sense. Or in other words, the basic idea is if you've got, I'll just take one of the pieces of wood. If you've got the overlap here and you've got some way to clamp this on the end, or maybe you are drilling a hole in there and then attaching a ring around it or something like that. Eventually, what's going to happen is the wood is going to fail. So maybe if you do attach a hook in there, it's just going to rip out of the piece of wood. And so before we even start testing the model, we've already kind of done this thought experiment and falsified our first model. So we've already made scientific progress and we didn't do anything. And we didn't collect any data. So maybe we hypothesize another parameter. And it's kind of quantifying the idea of diminishing returns. That, let's say, at a certain point, maybe it's here, that if you move any further, if you add any additional overlap, the wood is going to fail before the joint fails. And anything before this point, so I'll just keep my finger there. So all along here, the glue is going to fail, or the 2 pieces are going to separate before the wood itself fails. But at that point, that is my theoretical limit. So maybe we will call that parameter L for limit. And so maybe our model looks like this now. Tau times width times the minimum of overlap, or L. And again, because if you add more overlap, it's not going to increase the force. It's going to plateau at whatever L is. And that too has loads of implications. So that model proposes that force will increase linearly with the degree of overlap to a point. And then once it reaches that point, it flattens out. So you will get a function that looks like this. That's a very testable model. We could go out, collect data, and see if we see this noticeable kink. Or another way to express this mathematically is if your overlap is less than L, then the force is equal to tau, the holding power per square inch, times width, times overlap in inches. Whereas if overlap is greater than L, then that would say F max is equal to tau times width times L. And L is going to be a constant. It's just going to tell you how many inches of overlap you need before the wood breaks. And so in this statistical model, F max is also equal to the breaking point of wood, which is kind of cool. That's not nearly as specific as it would be in regression. I mean, supposedly you could figure out what the point of failure is for a statistical model, but it gets way more complicated to do that. But here it's kind of an accidental implication of the math. But then we start thinking about it. We're like, you know what? that seems weird to have this piecewise function where it's linear and then flat. And maybe we want a smooth function. And if you think about it, think of a game of tug of war. Like if you have, let's say, 2 people, one at each side. I mean, you can think of this as like a game of tug of war. And the degree of overlap is like the number of people. And so if you're playing tug of war and you've got one person on one side and one person on another side, if you add one person to one side, let's say, that's going to substantially increase the force relative to just one person. But now let's say you have 99 people and you add the same amount, just one person, you're not going to add all that much force. So it seems to make sense to me, again, not being a physicist or anything, but it makes sense to me that the relationship between overlap and force isn't going to be consistent. That the more you add, you're going to get diminishing returns. And so we might now have a function that looks like this. Force is equal to tau, again, holding power per square inch, times width, times L. And then we're going to multiply that by a proportion, but we're going to introduce a smoothing function. So we got the tangent, which gives us an ogive curve that looks like that. And so that is saying that all those factors are multiplied by how close you are to that limit. And how close you are to that limit is kind of non-linearized, such that initially, if you add a little bit more overlap, you get substantial gains, and then you get diminishing returns as time goes. So now, with each addition, we've added more complexity, and with this complexity, we've added more constraints on our model. And those constraints make it directly testable and falsifiable. So here are questions that we could ask now that we could never ask with a statistical model, or at least not easily with a statistical model. So now we could ask, is there a point of diminishing returns? What is the breaking point of wood? And you can make precise predictions, like how much overlap do I need to have 80% of the strength of wood? Or you can say, I am making a chair. I want it to be able to hold somebody who weighs this amount of pounds, which means I need the overlap to cover cases where pounds per square inch is equal to whatever. You can do that with this model. And you could also ask, is this better described as a piecewise or a smooth function? So I hope you can see that these mathematical models are far superior to statistical models, which is kind of weird. I'm a statistician. I do statistics. I use linear models all the time. So isn't that kind of hypocritical of me to say, hey, I use statistical models all the time, but I don't think they're as good as mathematical models? Maybe it is hypocritical, but there's a reason for that. And I think it has to do with the maturity of the topic that you're researching. So I am in a PhD doctoral program. And so that means in psychology, I would say, as far as scientific maturity, it's on the lower end. Like, we haven't discovered nearly as much about psychology as like physicists have discovered about how the world works. And so it doesn't surprise me at all that in psychology, we tend to use a lot of statistical models because a lot of our theories just aren't advanced enough that we can offer that level of mathematical precision. And I think that's a justifiable response, but I think the bigger reason why psychology and a lot of other disciplines don't use mathematical models is because they're hard. You have to have an understanding of math to be able to make them work. And you have to be able to translate your theoretical understanding of this topic that you're studying into mathematical functions. And that's where it gets a little difficult. But that doesn't mean it's not worth pursuing. I absolutely think we should pursue that sort of model. And there are lots of them out there. E equals mc squared. Force is equal to mass times acceleration. And I'm sure there are others. I just don't know them. So here's the take-home message. The more precise we are, and the closer we are to mathematical models rather than statistical models, the more specificity we have. And the more specificity we have, the more falsifiability we have. And it also yields to abundantly more information than just regular statistical models. So we went from saying more surface area means more force. Great. But after going through this exercise, we can now say much more interesting things like, what is the breaking point of wood? And what is the number of inches in overlap, at which point increasing more overlap isn't necessary? And we can also address why wood fails. Did this wood fail because of the glue or because of the wood? Those are things we didn't have much hope to answer before we developed a mathematical model. But again, they're hard. They require mathematical savviness. But they're transparent about their assumptions. They are easily falsifiable, which is a good thing. And I think this is exactly how science progresses, is by increasing the precision and increasing the falsifiability. So an actual question, how do you do it? You take a simplistics class, people, where we talk about statistical models. here I am thwarting my own desires to have you take a class with me. But that's okay. It actually is a good start. If you understand statistical theory and understand linear models, it makes it easier to make that transition to mathematical models. And my next live class is going to be January. I'm teaching mixed models by request. So make sure you sign up for that. And if you can't do live classes, and those are going to be held Mondays, I think, from 12 to 2 Eastern Standard Time. And if that doesn't work for your schedule, you could always do a self-guided class. I'll leave links to all those in the descriptions. But in the meantime, my fellow scientific modelers and whatnot, I hope you have a amazing day, and I'll see you next time. Peace out. Oh, da. Always thought that I'd learned a lot since graduate school, and I have. But I think I've forgotten just as much. I knew a lot of dude. Whew. I was smart in graduate school. Then I started taking weed, and now I've forgotten everything. Hey, you ain't gonna get a job unless you publish. If I teach, there's a difference, eh? Yeah. All right. I don't know. What do you think? You think we're ready to go? I think so. I think so.
One of my favorites. I get right into character.
Testing, 1, 2, 3. Let's see if that microphone is close enough to me. Audio test number 3.